Good day, everyone. This is part 2 of our discussion on natural products. In part 1, we discussed an overview on natural products. We distinguished primary metabolites from secondary metabolites, and we discussed natural products into categories according to their structure. We also talked about the different metabolic pathways on how secondary metabolites are synthesized. Before we proceed with our main discussion, let me just check if you grasped the concept of natural products already. So question 1, is the following statement true or false? Plants and other organisms synthesize natural products in order to provide beneficial substances for humans such as medicine. I'll give you a few seconds to think about it. This is a false statement because other organisms don't think about humans. They produce natural products because they found it evolutionarily beneficial for them. They evolved to produce chemicals against predators, against diseases. Basically, they produce these natural products because they want to survive in their environment. Nagkataon lang na may medicinal value din sa tao yung natural products. Next question. Coffee beans that are grown in different places taste differently. Does this have anything to do with secondary metabolites? Again, I'll give you a few seconds to think about this. The answer is yes, probably. Coffee beans taste differently when they are grown in different places because their secondary metabolite profiles are different. Coffee beans are not identical pag tinanim sila sa different places. Plants adapt depending on the environment. So, it depends on the climate or on the acidity of the soil or the predators present in a certain area, the age of the plant, and many other factors. So, plants synthesize different amounts of secondary metabolites depending on what their conditions are. So, for example, coffee beans grown in Sagada experience different conditions than those grown in Mount Apo. Thus, they will produce different amounts of secondary metabolites, and that is one factor that they taste differently. Of course, there are other factors na hindi due to natural products such as processing and handling. Okay? If you got those concepts, I think we are ready to continue with our lesson. In this video, we are now going to discuss how exactly scientists study natural products and how these are applied in fields such as medicine. Our outline for this video is as follows. For the first part, it is an overview of steps in natural product research, extraction, isolation and purification, characterization and structure elucidation, activity testing, and molecular modification. And for the second part, I will show you some selected techniques and technology. So, I will be showing you extraction and partition setups, isolation and purification techniques, instruments for characterization and structure elucidation. We've talked a lot about how natural products have all these interesting properties. These are due to their complex structures. That is why the ultimate goal of natural product research is finding lead compounds with beneficial effects. However, studying them comes with a price. The difficulty comes in when you scour for a potential lead compound in the many hundreds or even thousands of compounds found from the source. When you pick a leaf, for example, sobrang daming compounds dyan. Halo-halo na yung primary metabolites and yung mga secondary metabolites like terpenes, phenolics, alkaloids, and many more. Now, how are you going to handpick a good lead compound out of the sea of metabolites? So, I think it's time to define these steps in natural product studies. First is extraction. Okay, this is the process of separating a mixture of compounds from a matrix using a solvent. This is the initial step in limiting the compounds that you will work on. For example, you only want to work on water-soluble compounds from a plant. So, you will soak your plant material in water. You will get now your aqueous extract. Depending on the compounds that you want to obtain, you can change the polarity of the solvent. So essentially, tea and coffee are just aqueous extracts of leaves and coffee beans. Okay, next. Isolation and purification. Isolation is when a compound is separated from a mixture of compounds. Sometimes it can still be contaminated, so you need further purification. Isolation and purification are very important because, again, the goal in studying natural products is to single out potential lead compounds. Okay, third, characterization. Characterization is defining the physical and chemical properties of the isolated natural product. And when using more advanced equipment, you could even elucidate the structure, meaning you get to know the chemical composition, how atoms are bonded, and the functional groups present. This step is important to know or establish the identity of a substance. Who knows, it might be a newly discovered compound. Fourth is activity testing. In this, a substance will be tested for any pharmacological or biological activity. Inaalam dito kung ano ang effect nito sa humans and other living organisms. Is it antibacterial? Is it good for cardiovascular health? Is it anti-cancer? In this figure, it shows some of the pharmacological activity of polyphenols. And lastly, molecular modification. Sometimes, when scientists isolate a compound na may potential na maging medicinal drug, they can modify the structure by adding more functional groups to amplify its effect or to lessen its harmful side effects. For example, in this study shown here, aspirin, the structure is on the left, is the lead compound for designing new cyclooxygenase inhibitors. So, yung original structure ni aspirin, lalagyan ng iba't ibang functional groups at positions X, Y, and Z. Now, let me just point out that not all researchers will be doing all the 5 steps. So, let's take a look at some research papers on natural products. In this study, antimicrobial activity of supercritical fluid extracts of 2 Philippine medicinal plants, Psidium guajava and Euphorbia hirta. Implications to community health. So what they performed here are extraction and activity testing only. They used carbon dioxide supercritical fluid as solvent, and whatever they extracted from there, they tested it for antimicrobial activity on gram-positive and gram-negative bacteria. Okay, next. In this study, chemical studies on an endemic Philippine plant, sulfated glucoside and seco-A ring triterpenoids from Dillenia philippinensis. So they performed here extraction, isolation and purification, characterization, and activity testing. Okay, next, 5 new secondary metabolites from the fungus Phomopsis asparagi. They performed extraction, isolation, and purification, characterization, and activity testing as well, but they used different techniques. Okay, next, structure activity relationships of the antimalarial agent artemisinin. 7 direct modification of plus artemisinin and in vivo antimalarial screening of new potential preclinical antimalarial candidates. So they performed here, first ay molecular modification, then characterization, then activity testing. So kung mapapansin nyo, they did not do extraction and isolation anymore. You can do this if available naman sa market yung molecule that you will modify. Okay, next, analogs of disulfides from Allium stipitatum demonstrate potent antitubercular activities through drug efflux pump and biofilm inhibition. Okay, same thing, they did molecular modification, characterization, and activity testing. Okay, but they also use different techniques for characterization and activity testing compared to the previous one. Okay, we'll revisit these studies later, so just take note of them. Now let me just share this video from YouTube. The isolation of natural products, morphine and other alkaloids. So you might be able to appreciate the journey of natural product research. This video is a bit long, so I did not edit it into this lecture video, but I encourage you to watch it on your free time. The video covered a history of natural product research. So to summarize, they first analyzed the compounds in opium. So what they did was the poppy seeds were boiled in water and an aqueous extract was obtained. Then isolation was done by adjusting the pH level of the extract. A precipitate was formed, although it was not entirely pure. Purification was done through recrystallization. The purified compound was a white crystalline solid and it is now known as morphine. However, it took a few centuries to know its structure. Upon knowing the structure, it was then modified into a new, more potent compound, which is heroin. So the video covered all the steps from extraction to molecular modification. It was a well-made video, so I hope you get to watch it. Okay, going back to our outline, we are already done with the first part. So let's go to part 2, the more technical part. So bear with me here because at this point, mag-i-introduce ako ng medyo maraming bagong terms. I hope you won't get lost throughout the lecture, and I will also be inserting video clips so that you will visualize them better. These are the selected techniques and technology in natural product research. Let's go to extraction techniques first. What we will discuss under extraction are solid-liquid extraction and liquid-liquid extraction. Okay, so let's start with solid-liquid extraction. In solid-liquid extraction, the matrix that you want to obtain your compounds from is obviously a solid. So in this case, the solvent penetrates into the solid matrix by molecular diffusion. The soluble compounds can now transfer from the solid material to the solvent. There are many ways to do solid-liquid extraction, okay, and here are a few of them. So let's go first to maceration. This is the easiest one. Pag sinabing macerate, all you have to do is to soak the solid in the solvent. This could take more or less 48 hours of maceration to maximize extraction. Next, Soxhlet extraction uses a porous thimble loaded with the solid sample. It is placed inside the main chamber of the Soxhlet extractor. Then, the solvent is continuously heated and condensed. So, the condensed solvent will pass through the sample and extract the desired compounds while recycling the same batch of solvent throughout the extraction. The advantage of this system is that tipid siya sa solvent because it is recycled within the setup. It also takes a shorter time, around 2 to 3 hours only. This method is time and cost efficient, however, it cannot be used for collecting compounds that degrade with heat. So let's watch some video clips of Soxhlet extraction. Next is ultrasound extraction. Instead of physically agitating the solid particles to aid in the extraction process, ultrasound waves are used. The instrument used for this one is called a sonicator. We won't be going into detail in this one, but it might be interesting to know this. That's why I included it in the list. Next is steam distillation. This is usually used in extracting oil from plant material. In steam distillation, hot steam is forced through the matrix of raw material, opening the cavities in which the oil is held and volatilizing the oils, which will be collected in a separate glassware. So let's watch this video for a better picture of the process.
How steam distillation works. Most essential oils are produced by steam distillation. Steam distillation was invented around 1000 AD by Persian alchemist and healer Avicenna. It has been practiced for thousands of years since then and is still one of the best ways to take freshly harvested or dried plants and extract pure essential oil. Take a look at this distilling apparatus. The bottom reservoir is filled with distilled water. Above is an alembic chamber that holds the plant material, often called biomass. The biomass is full of tiny sacs that contain essential oil. When the water boils, the steam passes up into the chamber. As the steam passes through the biomass, the temperature causes the tiny sacs to burst open, releasing the essential oil. The essential oil rises up with the steam, and together the oil and steam pass into a tube. This tube passes through a cold condensing chamber. The cold temperature changes the steam back into liquid, which drips out of the tube. The liquid collects in a new reservoir, where the water and oil separate naturally. The water, which is called hydrosol, is left at the bottom, while the oil rises to the top. And lastly, the essential oil can now be collected and bottled.
The last technique that we will discuss under solid liquid extraction is supercritical fluid extraction. From the name itself, you can guess that the solvent used in this process is in its supercritical fluid state. The usual solvent is carbon dioxide. Because carbon dioxide is nonpolar, only nonpolar compounds can be extracted. But what's good about using supercritical carbon dioxide is that the resulting extract is free from toxic organic solvents. This process is usually used in extracting substances from food. For example, extracting caffeine from coffee and tea, or extracting carotenoids and fat from food products. Okay, let's watch this video for better visualization of the process.
The supercritical CO2 extraction process. Step number 1. The extraction chamber is filled with ground cannabis/hemp, also known as trim. Step number 2. The pump forces pressurized carbon dioxide at the optimal temperature and in the liquid supercritical state into the extractor chamber. Step number 3. The supercritical carbon dioxide acts as a solvent with the cannabis, dissolving the cannabinoid compounds it contains. Step number 4. The supercritical CO2 carries the cannabis oil particles past a pressure release valve into a separator. Step number 5. In the separator, the pressure is lower and the carbon dioxide separates from the cannabis oil. Step number 6. The carbon dioxide gas rises out of the oil and is routed back to the CO2 tank to be used again in a closed-loop system. Step number 7. The cannabis oil, waxes, and resins descend in the separator where they are captured in a collection vessel. Step number 8. The resulting substance is processed further into various products, free of any solvents.
Okay. Now we are done with solid-liquid extraction, so let's go to liquid-liquid extraction. This is also called partitioning. So this takes advantage of the fact that a compound can have different solubilities in different solvents. We will be watching a more detailed explanation in a bit. And we will also be watching how a separatory funnel will be used in this technique.
Now let's begin by comparing the behavior of two different compounds within the same system of immiscible liquids. So I've got two beakers here, and in the first beaker I'm going to add some water. And in that water I'm going to dissolve a fairly high polarity solute, so one that is relatively hydrophilic or water-loving. Now if I were to add to this another solvent, an organic solvent, which is immiscible with water, let's say something that's less dense, so it's going to ride on top of that layer. Over time, an equilibrium will ensue in which I have a distribution of my solute, a little bit in the organic and a little bit in the aqueous phase. But this equilibrium is not evenly distributed. There's more compound dissolved in the aqueous phase. Now let's take a look at what happens when instead I add an aqueous layer to my second beaker and then dissolve in that a lower polarity solute. Then to that mixture I'm going to add some organic solvent as well. And I'm going to allow an equilibrium to establish itself. But my lower polarity solute has a higher affinity for the organic phase than for the aqueous phase, so it tends to spend more time there. And hopefully what you can see here is that my higher polarity solute is concentrated more in the aqueous phase, and my low polarity solute is concentrated more in the organic phase. This is a behavior that I can exploit to separate the two from one another. Now let's have a closer look at that separatory funnel. Now, the separatory funnel has a Teflon stopcock at the base. This allows us to remove liquids by draining them out of the funnel. Now notice that little opening there in the tapered portion of the stopcock. When it's pointed in there where we can see it, that means the stopcock is closed. So I'll leave it in the closed position and return it to the iron ring. I'm going to add that solution of my compound and impurity to the separatory funnel while it's resting inside of the iron ring. The next step in the process is to give my impurities somewhere else to go. So I'm going to give it 50 milliliters of water, a solvent in which the blue food dye is far more soluble than butanol, but the 2-naphthol is not. I'll gently pour that in, which isn't really a requirement of the procedure, but I'm hoping to show you the process as it happens, so I'm going to be very delicate with this as I go. Now you'll probably notice that once I've added that water, I haven't really changed much. I still have sort of a green solution of naphthol floating above water because the density of the butanol solvent is lower. Before long, we're going to take a step that ensures that we'll get all of that blue food dye into the water layer. What I'm going to do is take my ground glass stopper and secure the top of my separatory funnel so nothing can come out the top. And the reason I'm going to do this is that I have to agitate my mixture. By holding the top closed and inverting the funnel, I cause many small inclusions of one solvent to form inside of the other. This speeds the process known as partitioning, in which each compound dissolved in my original butanol solution gets a choice. Does it want to be in the water? Does it want to be in the butanol? After I give it a suitable agitation, I let it rest. And placing a suitable collection vessel below, here I'm using an Erlenmeyer flask, I'll open my stopcock carefully and notice that the solution that drains out from below, of course, is the more dense water that contains only the blue dye. I'll watch carefully, ensuring that just as that thin layer of emulsion in the middle reaches my stopcock, I close it. There it is. Having stopped the flow there, I now have an aqueous solution of pure blue food dye. And finally, I'll collect my purified naphthol by adding a new clean collection vessel and opening the stopcock and allowing that solution to drain into that new collection flask. Notice again, we've got a yellow solution now. We've gotten rid of that blue impurity that was ultimately causing my product to look green.
Now I will just be showing you real quick the usual order of events in extraction of nat prod from plants. The flowchart is a bit small, but I hope you can read. So you start with your plant material at the very top and you subject it to solid liquid extraction. Usually, methanol is the extracting solvent. Methanol can extract a wide range of compounds because of its polarity. That's why it is usually used, and it is a cheap solvent as well. Next, concentration. In this step, you want to remove the methanol from the extract para mas maging concentrated. You use a rotary evaporator for this one. We will not be discussing how rotary evaporator works in this video, but feel free to look it up if you're interested. Then, you reconstitute the extract with water and place it in a separatory funnel. Okay, so, now you can begin liquid-liquid extraction. The order of solvents for partitioning will be in increasing polarity. So, first solvent is hexane. So, as you can expect, yung mapupunta sa hexane fraction ay yung mga non-polar compounds. So, these are your terpenes, or your lipids, and your sterols. The remaining aqueous layer will then be extracted with chloroform. Chloroform is slightly more polar than hexane. So, a little more polar yung mga mapupunta sa chloroform extract. Okay, then the aqueous layer is extracted with ethyl acetate. So, in general, semi-polar compounds yung mapupunta sa chloroform and ethyl acetate. Mas polar lang si ethyl acetate compared to chloroform. Okay, then lastly, extraction with N-butanol. Dito mapupunta yung mga very polar compounds such as tannins, saponins, and other glycosides. So after this liquid-liquid extraction, you can imagine na medyo na-limit na natin yung type of compounds per fraction. So from here, the methodology can now proceed with isolation and purification. First is isolation. Chromatography techniques are used for isolating compounds. We already discussed chromatography in the first quarter. I hope you still remember that there are different types of chromatography techniques, but the principles are the same. You have a stationary phase and a mobile phase. Solutes will travel at different rates across the column depending on how attracted they are to either mobile phase or stationary phase. This here is just a simple diagram of a chromatographic separation. So let's go to the first one in our list, chromatography using a glass column. This is the traditional method, and it is shown in this photo. So this type of chromatography separates components according to polarity. As you can see, the colored bands on the glass column represent different compounds. So may compound na mauunang lumabas from the column and it can be collected first, then wait for a little more before lalabas yung second compound. So that is one way to separate and isolate compounds. Next is preparative HPLC. HPLCs work under special conditions such as higher pressure and possibly higher temperature to achieve better separation. So meron tayong preparative HPLC that you can inject a larger amount of sample and you can recover them after separation. Analytical HPLCs, on the other hand, can only analyze small amounts, around a few microliters only. Thus, analytical HPLCs cannot be used for isolation. Okay, next, purification naman tayo. Let's go to something that you are familiar with already, distillation. So distillation only works well with volatile compounds because distillation separates substances according to boiling point. So this might work well with essential oils like terpenes and other lipids. Next, activated charcoal. Activated charcoal is a porous material made of carbon and it is able to absorb impurities from a substance. You can imagine the particles of activated charcoal like this with a lot of spaces in between for substances to absorb. It does not discriminate in what to absorb, so you will lose some of the product in this step. You might remember that this is also utilized in water purification for this reason. Next, recrystallization. Recrystallization is an important method of purifying non-volatile organic solids. It involves dissolving the slightly impure substance in an appropriate hot solvent. As the solvent cools, the solution becomes saturated with the solute and the solute will crystallize out, leaving the impurities in solution. So let's watch this clip to understand the concept better.
So recrystallization is quite a simple technique. It really just consists of dissolving a solid in hot solvent and then allowing things to cool so that it crystallizes again, but this time with very little of the initial impurity within the lattice. The trick is to choose the correct solvent that will allow this to proceed properly, since we need the solid to be relatively insoluble in this solvent at room temperature, yet soluble at higher temperatures. In addition, the ideal situation involves an impurity that is soluble at room temperature so that it remains in solution even when it cools and has no opportunity to precipitate along with the desired product. Or similarly, the impurity could remain insoluble even at the higher temperature so that once the solid dissolves, we can simply remove the solid impurity by filtration. Whatever the case may be, as long as the solid is able to dissolve and then recrystallize, the resulting crystals will certainly be of a higher purity than they were before, as it is inevitable that some proportion of the impurities will not be able to find themselves within the lattice as it reforms. So recrystallization is a powerful technique for the purification of solids.
Okay, last, this is just for emphasis, chromatography can still be used for purification. So there are times that one run sa column chromatography is not enough. So you can repeat chromatography to purify your sample. Next, let's go to characterization and structure elucidation. Let's go to the simplest one, which is melting point. This is only a characterization technique because it will not give you any idea about the structure. However, if you have a target compound, you can match the melting point of your compound with that in literature. So for example, you want to extract and isolate caffeine from coffee beans. You performed all the extraction and isolation methods and end up with a white powder. If your collected substance matches the melting point of caffeine in the MSDS, then you can conclude that the identity of your compound is probably caffeine. By the way, the melting point indicates purity. A pure substance will only have one value for the melting point. If impure, you will get a range instead. Next is UV-Vis. You can find the lambda max using this one. Remember, the max wavelength of absorption is more or less unique to a compound as well. So you can characterize a compound using UV-Vis by identifying its max lambda. So for example, caffeine has a lambda max of 272 nanometers as shown in this spectra. But of course, characterization is not enough because most of the important data is in the structure. So let's go to the next techniques for structure elucidation. FTIR. This is Fourier transform infrared spectroscopy. This uses infrared light. Different functional groups will absorb different wavelengths of infrared light. So you will see different peaks depending on the functional groups present. For example, this is the IR spectrum of 2-methacrylyl oxyethyl trimethyl ammonium chloride. And the distinct peaks for its different functional groups are as labeled. So using IR, you will know that this compound has OH, CH, C double bond O or carbonyl, NH, and COC or an ether group. This table here just shows the functional groups that correspond to the wavelength it absorbs. Feel free to pause this video if you want to take a closer look. But for now, let us continue. Mass spectrometry. This instrument gives the molar mass of the molecules and its fragments. Based on the fragments, you will get a fragmentation pattern and you will have an idea how atoms are connected. To help explain this further, let us watch a video.
Using a very small amount of sample, mass spectrometry, or mass spec for short, gives us information about a molecule's molecular mass, which is the added up weights of all its atoms. Inside a mass spectrometer, there aren't any air particles whizzing around, so it's a vacuum, like outer space. A sample molecule goes into a chamber, and the ion source generates a stream of electrons with a high temperature electrical current. In the ion source, a metal gets zapped, electrons get liberated, and that electron stream hits the sample molecule. This technique is called electron impact. It's a destructive approach, but also one of the most common in mass spec. When this stream of focused electrons strikes a molecule, an electron splits off from the molecule and it forms a radical cation. It leaves behind an unpaired electron, a radical, and it's a cation with a positive charge because the neutral molecule loses an electron. This radical cation is called the molecular ion. In an ideal situation, it flies down the tube of the mass spectrometer to the detector as is. However, electron impact is sort of like a bullet hitting a glass bottle, so sometimes the sample molecule is broken apart into other ion fragments. Any molecular ions and ion fragments are sent down a tube where a variable magnetic field sorts them by mass. This way, only particles of a specific mass can hit the detector at one time.
Next, circular dichroism. This is an absorption spectroscopy technique as well, but this uses plain polarized light. If you remember, chiral molecules interact with plain polarized light. So for example, depending on the orientation of the spectrum, malalaman mo kung R or S yung configuration ng compound. Of course, the more chiral centers, the more complicated the spectrum will be. Next, X-ray crystallography. This determines the arrangement of atoms of a crystalline solid in three-dimensional space. For the setup of X-ray crystallography, you take the crystal form of your compound that you want to analyze. Then X-rays will be made to pass through the crystal. The X-rays will then bend through the structure of the crystal. I think alam nyo naman that light that passes through very tiny slits will get diffracted, so you will end up with a diffraction pattern that is projected on the screen. So given the diffraction pattern, scientists will now be able to reverse calculate kung ano kaya yung 3D structure ng compound that gave rise to the particular pattern of diffraction. So that is the purpose of X-ray crystallography. Okay, lastly, NMR or nuclear magnetic resonance. This is kind of complicated, so maybe I can leave the explanation to this YouTube clip.
Nuclear magnetic resonance is a technique that uses magnetic fields and electromagnetic frequencies to study molecular structures. For high magnetic fields, superconducting magnets are used. Lower fields can be generated by permanent or electromagnets. Samples are inserted in the center of the magnet and are positioned in the NMR probe. So the sample is located at the position of the strongest field and highest homogeneity of the magnet. The NMR probe consists of coils that are used to excite the sample and record signal responses at radio frequency. The basis of NMR is that nuclei behave like microscopic magnets in a magnetic field. They spin around the main magnetic field just like a spinning top. This motion is called precession. The frequency of the precession is proportional to magnetic field strength. Additional local field differences are introduced by changing electron densities in a molecule. A higher electron density results in more shielding and thus a lower local field and lower spinning frequency. In NMR, the frequency of the excited nuclear spins can be measured from the electric current they induce in the coil. Fourier transformation of the time domain signals results in the frequency spectrum, with a signal for each different nucleus. The different frequencies we call chemical shifts, as they depend on the chemical structure of the nuclei. In practice, spectra are measured for all hydrogen nuclei at once, which results in the ethanol spectrum with 3 different peaks at different chemical shifts. Since nuclear spins behave like magnets, they also influence their neighbors. One way this happens is through shared electrons in the chemical bonds in the molecule. We call this J-coupling. Each spin can have two states, along the magnetic field or against the magnetic field. As an example, we look at the two methylene hydrogen spins, which are chemically identical. They can have four combinations: one spin down, one up, both spins down, one up, one down, two spins up. Each combination has a different energy level and influence on the neighboring spins, except that up-down and down-up combinations have the same energy level and influence. The influence is visible as a splitting of the signal of the methyl group into three. This is called a multiplet. Likewise, the three methyl hydrogen spins split the methylene response into four signals. In conclusion, NMR can identify molecular structures from chemical shifts and multiplets.
So in simpler terms, each signal corresponds to an atom and you will kind of know ano yung electronic environment niya. So from this, you will get the picture of what atoms are bonded to it or what atoms are nearby. So for example, in the NMR spectrum shown, the peaks are attributed to different carbons in this compound. If you are interested in looking for the different spectra of compounds, you can Google SDBS. It stands for Spectral Database. These are for organic compounds only. So for example, if you want to search for the spectra of menthol, meron silang available na mass spectrometry data. Okay, as you can see here, meron din silang CNMR data, and they also have infrared spectroscopy data. So in case you found the structure elucidation techniques confusing, ito yung summary table for them. Let's go through this para lang ma-differentiate nyo sila. So for mass spectroscopy, the compound is ionized and sometimes fragmented. Mass to charge ratio of ionized species are measured. Ang result, makukuha niyo yung atomic mass ng molecule and the fragmentation pattern. So for FTIR, IR light is absorbed by the compound. The wavelength of absorbed IR light is attributed to a functional group. So as a result, you will know what functional groups are present. For circular dichroism or CD, plane polarized UV-vis light interacts with chiral centers. Rotation of plane polarized light is reflected on the absorbance spectrum. So what you will get here is the stereochemistry and the absolute configuration of chiral centers. X-ray crystallography. X-rays are diffracted by the crystal form of the compound. Orientation of atoms in 3D space can be calculated from the diffraction pattern. So you will get the 3D structure using X-ray crystallography. And for NMR, nuclei precess in the presence of an external magnetic field. Each nucleus generates a frequency that is dependent on its neighboring atoms or even atoms 2 to 3 bonds away from it. So the result, you will get the connectivity of the atoms. So among the techniques here, NMR is the most powerful one. So if you are going to just use mass spectrometry or FTIR or CD or X-ray crystallography, hindi siya conclusive enough. Okay? You have to back it up with an NMR spectrum. Okay? But for NMR, standalone na siya. You can just safely conclude the structure of a compound from the NMR data. So as promised, babalikan natin yung studies na pinakita ko kanina. So for this study, ang extraction na ginamit nila is supercritical fluid extraction. So if you are interested in reading their extraction process, so you feel free to read that. So in this paper, yung extraction process nila, they did methanolic extraction for solid liquid, and yung liquid-liquid, gumamit sila ng hexane, ethyl acetate, 1-butanol, respectively. Okay, and for the isolation, they isolated 11 compounds and purified through different chromatography techniques. And for the characterization and structure elucidation, gumamit sila ng IR, UV, NMR, and MS. Okay, if you're interested, again, you feel free to read that. And this one, yung extraction niya, solid liquid, ethanolic extraction. Then yung liquid-liquid, partitioned with ethyl acetate only. So for the isolation, they used chromatography, normal phase, and size exclusion. For characterization, they used UV, ECD, IR, NMR, MS, X-ray crystallography, and TLC. So if you are interested in reading how they used almost all of the characterization and structural elucidation techniques that we discussed, so feel free to access that as well. And here, yung molecular modification niya, 50 analogs, and they were able to characterize the analogs using NMR, IR, melting point, and mass spec. And for this one, 16 analogs of disulfides, they characterized it using NMR, UV, IR, and mass spec. So there are a lot more NatProd research and studies out there. So you have a lot of reading material kung interested kayo. To end this video, just a summary, we discussed an overview of the steps in natural product research, such as extraction, isolation and purification, characterization and structure elucidation, activity testing, and molecular modification. We also discussed different techniques and technologies that aid in extraction and partition, isolation and purification, and characterization and structure elucidation. So that is all for this video. Thank you for listening.